Dear learners, welcome to the UGC lecture series on laser physics. I am Dr. Masilamani. I will now show you some of the simplest lasers available in the market with which you can appreciate the beauty and the importance of lasers. These are extremely simple laser and that will explain the facility with which you can make use of it for a host of applications. I told you in the first lecture that laser is a coherent light. The light beam is monochromatic and then it is directional and the wavelets are coming one after another in proper sequence. All these put together, we say in one word, it is a coherent light and that is a laser. Now, I can show you how, why and it behaves like this. Now, this is a torchlight, LED torchlight with which you are already familiar. I will just show you, it gives just an ordinary white light and you can see the beam comes as with this big spread of light, it comes like a cone of light. The second one is a violet or I would say purple color diode laser. It comes straight hitting your eye, but I am not showing towards eye. The next one is a green, my favorite laser. The fourth one is a red diode laser. This is the one which is commonly available in every toy shop. Now, we are going to do few more experiments with this. Now, what you see is a torchlight from LED. Remember, it is not a torchlight from the conventional bulb. What you see is a totally different thing and totally fascinating here. If you ever look at this torchlight, it will look whitish, but when I put through this one, you can see there it is a bluish light with the brim of white light. You know the reason? I tell you. There is no such white LED light at all. There is no such thing as a white tube light at all in principle. What is happening is, if you analyze your regular tube light, which I see it in my house, in your house, now what you saw is a white LED light. Remember, it is not the white torch light with which we are familiar about 10 or 20 years ago. In the conventional torchlight which security or police officers or your parents used, they employed a small bulb in which the wire was there, current was flowing through that one. So, it heated up the wire and then it produced yellowish light, that is a thermal light, which is totally different from what you have seen today, which is the modern torchlight. In this case, it is the LED which is producing light. There is no such thing as a white LED in principle, and that is shown by the features on your TV. What you saw is a blue light with the halo of white light. What it means is this, just listen carefully, you will appreciate it. The light that really comes out from the LED is only a blue LED light at 450 nanometer, which I have measured many times. But what is happening is, the light that comes out is absorbed by a fluorescent material and then the fluorescent material produces light in a band of wavelength from 450 to 750. So, it is a patch of light. It is a 450 nanometer LED induced fluorescence light is what you see eventually. This is something similar to what is happening now in your household tube light of 1 meter length. What is happening is, you have one end a filament which is a negative cathode, the other one is anode. You apply voltage about 220 volts, then electrons are kicked from one end to another end, or electrons are attracted towards a positive pole. So, they get accelerated. During this acceleration, they acquire enormous energy. They are trying to go and reach the anode, they are not interested in producing light for you. On the way, they come across a number of mercury vapor atoms. those mercury vapor atoms get excited, and then when they come down, they produce emission. They produce emission at different wavelengths, the most important being 365 nanometer, which is ultraviolet, and 408 another violet, 428 another blue light, and there are so many other lights including 541 green light. All these are discrete spectral lines emitted by the excitation and de-excitation of mercury vapor. These are discrete lines, they never produce white light. Then what happens is, on the fluorescent tube there are certain fluorescent material coated which absorb green, ultraviolet, whatever it is possible, it swallows them up and convert things into a white fluorescent light, and that is what you get in mercury vapor. The same idea has been used up in this case also. That is the first step. Second step, which is important for today's discussion, is what you saw is a big patch of light with a diameter of about 10 centimeter at a distance of 1 meter, which means what is the divergence of this one? If I say 10 centimeter is the diameter, radius is about 5 centimeter, that is 50 millimeter. This is the divergence over a distance of 1000 millimeter. So, 50 by 1000 will be 50 milliradian is a divergence of this LED white light. In contrast, what you are going to see in the next one, we will show you 3 types of laser. One will be a violet laser or purple, the other will be a green laser, the third one will be a red laser. In all these, look at carefully, none of them is circular, all of them are elliptical. That is, in the length wise they are all typically 4 millimeter and the breadth wise about 2 millimeter approximately. I am telling you all these are approximate to get the feel of it, you can measure it later when you do in your experiment. That means, coming back, take any of the laser over a distance of 1 meter, 1000 millimeter, the divergence on the horizontal direction is only 2 millimeter over a distance of 1000 millimeter. That means, the divergence is 2 over 1000, 2 milliradian. Compare it with your own LED light, that is 50 milliradian, and this is only 2 milliradian. This is what you say, this is why you say laser is a directional beam, it has a extremely small divergence. This is true for red laser light, blue laser light, green laser light, more or less there may be small difference here and there, that is one thing. Second point, if you have the opportunity, you can look at the polarization property also. You can put a polarizer there and then you will see all the laser that comes out from any of the diode laser is polarized, because the laser comes out between the p-n junction diode, and the junction diode is something like this. You can say this is a p diode and this is a p and this is n, and the edge is the p-n junction. The laser is coming out from this edge, that is why what the laser comes out is a strip, like a rectangular strip, approximate elliptical strip. Not only that, since this is a solid state material, the refractive index is greater than 1, you must think about Brewster law. and you know tan theta is equal to 1 over mu if I remember correctly. If you calculate, you will see since it has a refractive index, automatically this will polarize the light. That is why all solid state lasers, when they come out, is polarized. This is not true for a helium ion laser, because ordinary gas lasers by themselves cannot produce polarized light unless you introduce something called Brewster windows. We will see that detail later. Next point, very important point. If you look at the laser by itself, you will see when it falls on a rough surface like a paper, twinkling a light. And this twinkling of light is what we call a speckle, and the same speckle what you saw when the light was passing through a smoky cloud. We showed this one, which is, and then you will see the twinkling is due to speckle. What is that speckle? Let me explain in a minute, you will understand. Every surface has certain up and down, it is not a smooth. The laser light, which is a coherent light, when it falls on up and down, it comes to reach your eye at certain path difference, certain phase difference. Whenever the like two wavelets with difference in path difference come, they will produce interference. Interference means darkness and brightness, high amplitude and low amplitude. Because of this one, you will have interference, and since the surface is at random, you will see random interference in your eye is what happens called speckle, that will give a very fine silky smooth twinkling. I mean, it is very difficult to explain, words fail to see the beauty of speckle, the real beauty of laser. It will show an extraordinary property of twinkling all the way because of the speckle property. These are the two important properties. First thing, speckle, twinkling, directional, single wavelength. There is one more thing, which is coherence due to phase correlation, that cannot be shown immediately unless we have certain other additional instrument, which I am not able to show now. With this, I would say you would have got the main features of a laser. Now remember, people often say working with a laser is dangerous. Why? The reason is simply this: since the laser is very directional, when it hits your eye, the eye has a lens. The lens will focus that light, fall on your retina, and then burn a hole, or at least make uneasy feeling. You will not be able to see things very easily after some time having seen a laser light directly into your eye. So, this is the big security risk. Don't ever shine a laser on the eyes of anybody else or on your also. That is the only danger with most of the ordinary diode lasers. Ordinary diode laser, if it falls on your hand or your skin, no problem. Particularly the red diode laser available in the market. The green laser, which is really powerful, it is about 5 or even 10 milliwatt available, which is expensive, that will make a certain burning sensation. That burning sensation is reasonable. Immediately you will feel something is burning, you will take your hands off. That is all the danger. When you go for high power lasers like neodymium YAG laser or a carbon dioxide laser, if it falls on your hand, it will really burn. There is certain laser called CO2 laser, high power CW 10 kilowatt CO2 laser, which can just cut your finger like a knife cutting a banana or a chili. It is so powerful. They have different application. Ordinary students are not allowed to go and work their laboratories. They are meant for experts, not for students. But I want you to know such powerful lasers are there. The size of a big CO2 laser is available in indoor. It is so big, it is the size of you. What I am showing is a small tiny. This has its own application. This kind of diode lasers are extraordinarily suited for communication. In fact, for communication, none of the other lasers are useful except infrared laser and red diode laser. So, they are something like made for each other. I will show you simple experiments. The most important interesting experiment is the diffraction. I will show you how light gets diffracted in a grating. I will show you with the purple light, green light, and then also with the red light. You will see the separation between the 0th order and +1 order and -1 order, +2 order and -2 order changes dramatically as the wavelength changes. This is something I want you to look at it, and then I want you to interpret also. That is first thing. Second point is, I am going to show you another very interesting experiment. When I shine the laser on a zone plate on a Fresnel's lens, this particular Fresnel lens is kept, look at this one, it is big lens like this one, it almost like a flat one. If you ever buy this one, these are all available in the toy shops these days. This I bought it in a book fair, so simple one, and this is something I really love it because it is a Fresnel zone plate. Fresnel, a top class scientist, predicted that if you draw circles one after another with a certain path differences, that will do something effectively as a convergent lens. This is called a zone plate, and this will be able to produce a big patch of speckle which you will see in the experiment. With this, let me sum up what has happened in this particular session. We had been able to show some of the simplest experiments with the 3 different laser diodes. A purple one which is about 405 nanometer, other one 530 nanometer green laser, the last one is 650 red diode laser. All of them have a power of about 1 to 5 milliwatt power. All of them are continuous working lasers and all exhibited very good monochromicity, very low divergence, and they are all very coherent lights. All these properties have been already explained in my earlier lectures. I have been able to show you the importance of diffraction, importance of polarization. With this, this particular aspect will be closed. In the next session, I will go more into the theory of a laser. What is meant by spontaneous emission, what is meant by stimulated emission, what is the contribution made by Einstein in this particular domain, and how to make a laser. And laser, you must have heard about it, it is a light amplified by stimulated emission of radiation. That is what the expansion of the word. From that, you all imagine that laser is a light amplifier, but in practice most of the lasers are not amplifiers, they are laser oscillators. What is the difference between light amplifier and light oscillator? All these things will be explained subsequent lectures. Thank you very much.